Hello everyone, and welcome to the Linear Regression Project Exercise Solutions lecture. In this lecture, we'll begin to go through the solutions for the linear regression project. Let's go ahead and get started by jumping to a Jupyter notebook. Alright, here I am at the notebook. Let's go ahead and get started. First thing we need to do is all our imports. I'm going to go ahead and import pandas and NumPy. And then I will also import my visualization libraries, matplotlib.pyplot as PLT and seaborn as SNS. And then since I'm using a Jupyter notebook, I also want to make sure to set matplotlib inline. And as the instructions said, we'll go ahead and import scikit-learn as we need it. Then we want to get the data. Since we're going to be working with the e-commerce customer CSV file from the company, it has those 4 columns, so let's go ahead and read it in as a data frame called customers. And say pd read CSV, and then we can start typing what we want, and if we just click tab, it will autocomplete for us. And then let's go ahead and check out the head of the data frame by saying customers.head. And hopefully by now you're pretty used to this sort of interaction with a data set. We notice here we have email, address, avatar. We can scroll over to the right to see the numerical columns, such as average session length, time on the app, time on the website, length of membership, and yearly amount spent. We can also check out the describe method to get some statistical information off of the numerical columns. And we can do info to just get some basic information, such as the object types, how many entries there are, how many columns. So it looks like we have 500 rows of 8 columns. Now let's go ahead and begin to do some exploratory data analysis. And for the rest of the exercise, keep in mind we're only going to be using the numerical data of the CSV file. First thing we want to do is use seaborn to create a joint plot to compare time on the website and yearly amount spent columns. And does this correlation shown make sense? Let's go ahead and do this. The plot should look something like this. Don't worry if you weren't able to get the exact coloring, but we can say SNS joint plot, and we want to compare time on a website and yearly amount spent. Let's go ahead and specify that our data is going to be the customer's data frame, and then X is going to be time on website, and Y is going to be yearly amount spent. And there it is. As far as trying to interpret this sort of scatter plot, there doesn't appear to be a clear trend between time on a website and yearly amount spent just by looking at this visually. We'll go ahead and take a look at this later on when we actually start building our model. Let's go ahead and move on to doing the same but with the time on app column instead. So basically we want to, as shown here, say time on app is the X and yearly amount spent is on Y. And we should see a little more correlation here between time on app and yearly amount spent. We'll do this by saying joint plot. Again, you set your data equal to customer, and it doesn't really matter the order of these arguments as long as you specify which parameters or arguments you're actually passing in. So I want to say time on app and yearly amount spent. And remember, the spacing needs to be, and capitalization, all need to be exactly the same as the column name. So for instance, customers wasn't correct, and I need to say data equals customers. Okay. And here we have the same plot. It looks like there begins to be some sort of correlation between increased time on app, increasing yearly amount spent expenditure. Let's go ahead and use joint plot to create a 2D hex bin plot comparing time on app and length of membership. We can do this again with joint plot, specifying X is equal to time on app, Y is equal to the length of membership column, and then we'll specify kind is equal to hex in order to create a 2D hex bin plot. And finally, we want to say data is equal to customers. Run that, and now we see the hex plot. Great. Let's go ahead and explore these type of relationships across the entire data set using pair plot to recreate this plot below. And don't worry if you don't get these exact same colors. You can just say SNS pair plot and then pass in your customer's data frame. run it. It may take a little bit of time depending on your computer since it's a larger data set, but we should get something that looks like this. And based off this plot, what looks to be the most correlated feature of yearly amount spent. So we can go ahead and check out the yearly amount spent column, which, depending on whether you're looking on the X or Y axis, is right here at the very bottom. So yearly amount spent, if we just look at this visually, it looks like right here is the highest correlation, which looks like more of a straight line, and it's the length of membership. So the answer to this question, just based off of this visually, is length of membership. Now what we want to do is create a linear model plot using Seaborn's LM plot of the yearly amount spent versus length of membership to actually try to plot out that relationship in a little more detail. And we can go ahead and say SNS LM plot, where we want X to be the length of membership, Y is equal to yearly amount spent, and data is equal to customers. We'll go ahead and run this, and we got the exact same plot out. Now notice here, there seems to be a good linear fit on this data, and you can notice that because there's very little error as far as these error bars go. So already we know a pretty good idea that the longer you stay a member, the higher yearly amount expenditure you're going to have, which kind of makes sense. Now let's go ahead and create our training and testing data. We'll go ahead and start this by setting a variable X equal to the numerical features of the customers and a variable Y equal to the yearly amount spent column. Let's go ahead and see our column names by saying customers.columns, and this is going to make it easier than having to type in a bunch of information. So I can go ahead and say Y is customers, and what we're trying to predict is the yearly amount spent. And I would just go ahead and tab autocomplete that. And then for X, what we want are the numerical columns. And that's going to be equal to average session length, the time on the app, the time on the website, the length of the membership. Let's go ahead and put that in. So customers, and then pass in a list of the column names. We can go ahead and put this on one line if we wanted to. You can also separate it into multiple lines as well. But here we go, and that should give us the numerical columns. Okay, great. So we have our Y data and our X data. Remember, Y is what we're trying to predict, and X are the numerical features for this. What we're going to go ahead and do next is use cross-validation train test split from sklearn to split the data into a training and testing set. And we'll set the test size to 0.3 and random state equal to 101. Okay, you're going to be doing this all the time during the machine learning section, so eventually you'll just have this memorized, but we're going to say from sklearn cross-validation, and you can do tab to get these options, import test train split, and actually it should be train test split before I run this. Train test split, and you can do tab, which will let you know if you're doing the correct thing. And then we'll go ahead and say, what I like to do is train test split, do shift tab, see the full documentation string, scroll down until you come to the examples, and then you'll see an example here. Go ahead and just copy and paste this. And this kind of saves you a lot of typing. And now what we want to do is set the test size to 0.3 and the random state to 101. You don't have to set the random state to 101, but if you do want to have your results match mine in the solutions notebook, you should set the random state. Otherwise, in normal circumstances, you can just leave it with the default random state and not add that parameter. Let's go ahead and run this and make sure everything worked out correctly. Great. Now it's time to train our model on our training data. We're going to go ahead and import linear regression from sklearn.linearModel. So what we want to do is say from sklearn.linearModel, and you can do tab autocomplete, import linear regression. And then we're going to create an instance of a linear regression model named LM. Hopefully this feels really familiar given the lecture series. We'll go ahead and create that object, and then we want to train/fit LM on the training data. And we do this by saying lm.fit, and if you do shift tab here, it'll tell you what order you want X and then Y, And since we're just dealing with the training data, we want xtrain, ytrain. We'll go ahead and fit that, and now we have our fitted trained linear regression model. What we're going to do now is print out the coefficients of the model. And we can do that by saying lm and start typing coefficients, and eventually you get coef underscore, and this returns the coefficients as an array. All right, let's go ahead and move on to predicting from the test data. And now that we have a fit model, what we can do is evaluate its performance by predicting off the test values. So we had to use lmpredict to predict off the x test set. And we can do lmpredict, pass in x underscore test, and set the results equal to an array called predictions. And then we want to create a scatter plot of the real test values versus the predicted values. So we can go ahead and say plt scatter, pass in ytest, and then pass in predictions. And we can say plt, we'll go ahead and do some labels here. We'll say x label. Remember, x is our ytest, the true values, and plt y label is the predicted values. And if we go ahead and run this, notice that our model is actually doing quite well. If this was an absolutely perfect straight line of all the dots on top of each other, it would mean we had a perfect model on the test data. But for now, we can see that there is a little bit of noise and error, but it's honestly pretty good considering y-test versus predicted values, and that we were just using 4 numerical columns. Okay, let's go ahead and actually evaluate this model, not just visually, but through some mathematics. So let's evaluate our model performance by calculating the residual sum of squares and the explained variance score, which is r squared. Remember from the lecture that we can do all of this just by calling from sklearn, import metrics. We can start by saying print MAE for the mean absolute error, and I'm going to go ahead and then call metrics dot mean. In this case, we want absolute error, and we just pass in the y-test, the true values, versus the prediction values. Let's go ahead and just copy and paste this since we're going to be using it quite a bit. In the same cell, I can say print MSE metrics dot, and in this case, we want mean squared error. And I'm just going to copy and paste y-test predictions. And then we want RMSE. And we want metrics dot, and in this case we want the, we want the mean squared error again. Pass this in, but remember, since this is the root mean squared error, we're going to go ahead and say np sqrt and take the square root of that. Let's go ahead and make sure this runs correctly. Great, and it looks like we got matching results. Now you'll notice there was another little issue here that said and the explained variance score. Now this wasn't actually referred to in the bold instructions. It was kind of a bonus for you to discover this on your own. But what you can do is say metrics dot, and if you start typing EX and do tab autocomplete, you'll also get explained variance score. And this is the R squared value for a regression fit. And you can pass in again y-test and their predictions and see how it ran. So let's go ahead and check that out. And we get 0.98. So if you're not familiar with R squared, that's basically a measurement of how much variance your model explains. And we explain about 99% of the variance. So you can see we have a very good fit model, especially on the test data. Now let's discuss residuals. So we should have gotten a very good model and a good fit, like we just saw. And we're going to quickly explore the residuals to make sure everything was okay with our data. We're going to plot a histogram of the residuals and make sure it looks normally distributed. And you can use either a plt.hist or seaborn this plot. We can go ahead and say, just doing seaborn, sns.thisplot, and we want to say y-test minus the predictions. Whoops, let's fix that. And we'll go ahead and specify bins to be a little bit of a larger number. And we get our distribution. So it looks pretty normal, given what we've been working with. And we already know we have a very good fitting model, so we shouldn't be concerned about the residuals. And as far as this conclusion, we still want to figure out the answer to the original question, which was, do we focus our efforts more on mobile app or website development? Or maybe that doesn't even really matter, and membership time is what is really important. And what we're going to do is see if we can interpret the coefficients at all to get an idea. We're going to head and try to recreate this data frame below. We did this in the lecture, or a similar data frame in the lecture. Let's go ahead and do that. We pass in the coefficients as our data, and we say x.columns as the names. We'll call this CDF. And let's say CDF.columns. And we can actually just pass this in while we're creating this. So we'll say columns is equal to, we'll say coef. Let's go ahead and check CDF, and we get the same data frame. All right. Now the question is, how do we interpret these coefficients? And there's a little markdown cell in case you want to type here, but you don't have to. You can just think about this in your mind. But basically, the way to interpret these coefficients is one at a time. So, for instance, average session length. If you hold all the other features fixed, a 1 unit increase in the average session length is associated with an increase of around $26 more spent. And similarly, an unit increase on the time on the app is associated with an increase of $38 spent per year. And time on a website is actually just shown to be a 19 cents increase, which isn't so great. And length of membership, by far the strongest feature here. If you hold all other features fixed, a 1 unit increase in length of membership is associated with an increase of around $61. So now the question is, do you think the company should focus more on their mobile app or on their website given this information? Now this is actually tricky because there's two ways to think about this. If you look at your coefficients and the data in our model, we could develop the website to catch up to the mobile app. So one way of thinking about this is, oh, well, the website needs the most work, and that's where we should focus more of our efforts. Or you could think of it another way, which is you should develop the app more, since that is working already much better. And this sort of answer really depends on a number of factors going on at this particular company or wherever this data is actually coming from. And you're going to have to want to explore the length of, or the relationship between length of membership and the app or the website before coming to a conclusion. And this is truly where the role of a data scientist starts to blend in with the role of someone with a little more business acumen and it's more familiar with the management, how much it's going to cost to improve the app versus the website, etc. So all these choices are going to have costs associated with them. And without that information, it's a little hard to tell. So what you can do is report and show this information and display it in an informative manner, but you're going to need more information on the cost of the decisions to actually choose a correct focus. But at least now we have a fully informed background to make that decision. All right. I hope you enjoyed the project exercise. Hopefully, if you need any review, you can check out either the solutions notebook or review the lecture, which kind of lines up to the linear regression project. Again, this data was not real, it was artificially created, but as we move along now throughout the machine learning section, we're going to begin to focus more on real data sets from real-world problems. All right. Thanks, everyone, and I'll see you at the next lecture.